important for us to have befitting survey parameters or survey plan before we embark on geophysical survey. The target we are going to map, or what is of interest to us, the sources rest on how we have chosen our survey parameters. What are those or some of those things we need to know? We need to have an idea, like I said, of the nature of the target, the geology, what kind of spacing are we going to use between the transmitter and the detector or the receiver. To a very large extent, they will help us in mapping a target or any anomaly of interest to us. Essentially, too, we said the physical property of that material as it varies from the surrounding, which we simply call contrast in physical property, is also very important when we are embarking on geophysical prospecting. I did mention that if we are using, for instance, gravity method for prospecting, we have to take measurement of gravity data from one place to another. For gravity to be successful, there must be contrast in density. There must be lateral variation in density. This variation in density makes gravity method or gravity techniques to be a viable tool in subsurface investigation. If there is no contrast or there is no difference in gravity, there is no difference or contrast in density, there will be no need for us to use gravity method. In other words, the anomaly, the target will not be detectable because there is no contrast in density. So for us to be able to detect a target, there must be a contrast, or we need to have knowledge of variation in physical property of the material. As you are going to continue in the department, you will be seeing work that have been done by several researchers as regard this physical property that have been measured. If, for instance, it is sound, and I'm using electrical resistivity method, some researchers have given us range of value of resistivity that can tell us this is sound, range of value of resistivity that can tell us this is granite, this is sedimentary. What kind of rock we have? Is it the consolidated or the unconsolidated? Several work have been done to give us standard for this value. So if we know the standard and the value we have obtained after we have processed our data, we now make reference to that value. Oh, this is the range of density that I have. This range of density show, for instance, I've encountered water. For instance, we want to look for water and I want to make use of seismic method. After I have analyzed the seismic data and I'm having a velocity that lies between 1004, 1005, 1006 to about 2000 meters per second. That is the area of interest. I know in that layer, that is where the water is. Whoever is going to drill I can now tell them, based on the physical parameter of the subsurface that we have measured, the velocity at this depth of so and so, at a depth of about 35 meters, the velocity that we obtain lies from 1,500 to 1,700. That is the region where water lies in the subsurface. Please drill to that layer. That is physical parameter assisting us to infer the geology of the subsurface. Oh, the velocity we get is in the neighborhood of 400 meters per second. You cannot get water in that layer because that layer is full of air. So that is how physical parameter help us in inferring the composition of the subsurface.
They are telling you to be careful.
Another one. I've told you when you are joining, please ensure you are muted. I will just remove you from the class. I've just done that to 2 students now. Mute yourself while you are joining the class. So in order for a target to be detectable, the secondary feed, in the last class, on the whiteboard, I drew the ground surface. I drew a transmitter, which is what sends signal into the ground, a receiver, which receives or it gets the response from the target. Between the transmitter and the receiver, and they are separated by a particular distance, the transmitter sends a signal from the ground into the earth, from the surface of the earth into the ground. That signal that it sends is going to encounter so many materials. Because it is encountering so many materials, we call it the primary field. Modulated primary field. Why is it called modulated? It is called modulated primary field because it encounters many materials in the subsurface. There will be another signal that will travel only on the surface of the ground. That is unmodulated. So we are only bothered with the signal inside the ground. In some other geophysical survey, the one that travels on the surface of the ground, the unmodulated one, is what they will be interested in. But as far as we are concerned here, we are interested in that primary signal that goes into the subsurface. From the transmitter, it travels into the ground. We call it the modulated primary feed. When that primary feed reaches a target, a conductive target, the magnetic field will be changed into current. And some of this current will be noisy. And that noisy current is what in your basic physics you call eddy current. According to law of electromagnetic induction too, that current that gets to that target will be changed to magnetic field again. That magnetic field is called secondary magnetic field. The secondary magnetic field will now travel from the target and we get to the receiver. So that is what we call the primary field and the secondary field. the target in the subsurface. While the signal between the feed between the target and the receiver, the detector, is what we call the secondary feed. That is also a method you are going to learn when you get to your year 3 in the department. So in order for a target to be detected, take your mind to that diagram I drew. The secondary feed, which in this case I will call FS. I will call the secondary feed FS. I will call the secondary feed, or let us call the secondary feed FS. Let's call the secondary feed FS. F superscript F. S. F superscript, that is secondary feed. So in that slide, in this material, when you see F superscript S, it is secondary field. Then when you see FP, it is the primary field. Understand what the primary feed is. Then when you see FT, that is the total feed. That is the total feed. The total feed is the sum of the primary feed and secondary feed. So F superscript T, or FT, is the total feed, which is summing the primary feed and the secondary feed. So in order for a target to be detectable, the secondary feed, whether that be the electric feed, which is what you are also going to do in your year 3 electrical method in geophysical prospecting. The magnetic field is also what you are going to learn in your year 3 in the department. Must be larger than the noise. So the secondary field, be it electric field or magnetic field, must be larger than the noise, or geological noise or instrumental noise. So the noise is usually spurious. We refer to noise as spurious. There are so many materials or so many things that could be responsible for the noise. For instance, if we are embarking on magnetic survey, we want to measure variation in magnetic property of the earth. We want to measure variation in magnetic property of the earth, or there is iron ore deposit in the subsurface. We are now contacted as Geophysics group to help map that iron deposit. We have to leave Lagos to maybe Kogi State for the mapping of iron ore, for instance. Because we have been consulted, and for that consultancy to be executed, we are going to make use of magnetic method. We are going to take our magnetic equipment to Kogi State because we want to map iron deposits in that area. There are so many things that can affect the iron deposits that we want to map in that area. For us as geophysicists that we want to map that iron, we must ensure that anything that is also magnetic, anything that magnet can attract, is not with us. You want to carry out magnetic survey and you are wearing a belt that is made of iron. That belt you are wearing and you are carrying the instrument is going to affect what we are going to measure. So that belt that you are carrying about while we measure the variation in magnetic field of the earth is regarded to as a noise. Where we are collecting the magnetic data, we have power lines. There is power line in that area, and yet we are still collecting the data. The power line will also affect the data we are collecting. As we are collecting the magnetic data, it is about to rain, and behold, there is thunderstorm. And we still continue with the data collection. the thunderstorm, the magnetic storm, they are going to affect our data. The data we collect while there is a thunderstorm or magnetic storm, the storm is regarded as noise. The best we could have done is to suspend the data acquisition when we know it's about to rain, so that we don't involve noise in our data. So when you get to your year 3, you start specializing in one aspect of geophysics or another, and you see geophysics and geology to be interesting. So the secondary feed that we are going to record must have the amplitude of that secondary feed must be extremely large, must be larger than that of the noise, so that we can identify this as noise and we remove it. So it must be relatively large enough compared to the primary feed. The secondary feed must be relatively large enough compared to the primary feed. For example, if the noise in the primary feed is anticipated to be 5% and the instrument sensitivity is 5 millivolts, then the secondary feed must at least be above 5 millivolts in order to detect the target. To do this now, we must provide two parameters for measurements. What are these two parameters? Relative difference and absolute difference. Relative difference and absolute difference. How do we estimate relative difference, ROD, and absolute difference, AD? Relative difference is the ratio of secondary feed to primary feed expressed in percentage. Relative difference, again, is a ratio of secondary feed to primary feed expressed in percentage. So if we know the secondary feed as well as the primary feed, and we divide the secondary feed by the primary feed, then we get what is called the relative difference. The absolute difference is Fs divided by Ft. Please, I have omitted this. Can you rewrite that? The absolute difference, AD, is equal to Fs divided by Ft. The absolute difference is Fs, which is the ratio of secondary feed to the total feed. The ratio of secondary feed to the total feed. While the total feed is the sum of the secondary feed and the primary feed. To test whether a target is adequately detectable, given certain survey layout, we use forward modeling. This is also a term that we use when we are before we embark on geophysical survey. So for us to know how adequately our target has been detected in a given survey, we have to make use of forward modeling to compute the primary feed using a model. that does not contain the target and the total field using a model that does contain the target. Now, let us look at this. For us to test whether we have been able to detect a target during a geophysical survey, we have to make use of forward modeling. Forward modeling is used to calculate the primary field. Forward modeling is used to calculate the primary field, or we use it to calculate the physical property of the subsurface using a model that does not contain the target. What do we mean by this forward modeling? Let me go to the whiteboard. Let's go to the whiteboard so that we can understand the idea of modeling. Okay, that's come up now. We were signed out. So we're looking at forward modeling, and to have an understanding of that, let us go to the whiteboard to model data, or the model second ring, we have the data space.
上地形说弄，还康体现在没有，啊，有的啦，不用搞，不过是都已经讲，
Okay, so we are back. We are looking at forward modeling. So forward modeling. So this involves the prediction of the geophysical property, the prediction of the geophysical responses like seismic, like seismic waves or magnetic field based on a known or assumed model of the Earth's subsurface. So this is what forward model entails. So to do that, I want to draw two circles. These are two oval. In the first one, I have what is called model space. This is model space. I'll create a model here. And here, I have data space. This is data space. In this model space, I assume a model of the Earth. I assume a model of the Earth. For that model that I have assumed, I assign some value to it. After assuming some value to it, then whatever I will get is data space. So when we move from model space to data space, that is what is called forward modeling. When we move from model space to data space, I assume a model of the subsurface. I will now calculate the variation in parameters of that model that I've assumed. For instance, I assume this as a model of the subsurface. I have the first layer density, ρ1, or resistivity. I have the first layer density, ρ1, and the thickness h1. I have the second layer density, ρ2, and thickness h2. Sorry, this is h1, and thickness h2, and so on. This is assuming hypothetical model of the Earth. If I now calculate the response by measuring the velocity, this velocity that I have obtained is what we regard to as forward modeling. So in forward modeling, we calculate the distribution of the subsurface parameter. That is FM, forward modeling. If on the other hand, I want to reconstruct the true model of the subsurface, I will now go from the data space back to the model space. So when I move from the data space to the model space, in order to reconstruct the true model of the subsurface, that is what is called inverse modeling. We call that inverse modeling. That's an inverse modeling. In the case of inverse modeling, we simply move from the parameter that we have measured. We now use that parameter to obtain the true parameter of the subsurface. So in other words, we use the model we have obtained, the data we have obtained, to reconstruct or to recover the exact model or the true model of the subsurface. So in the case of forward modeling, I will change the density, I will change the thickness, I will look at what response I will get. I will change the second layer density, the second layer thickness. I will look at the response. I will change the third layer density, the third layer thickness. I will look at the response. So that way is what is called forward modeling. Having obtained those parameters, which we call model parameters, having obtained the model parameters, if these model parameters are now used to reconstruct the true model of the subsurface using some algorithms, that is why coding is essential in geophysics, using some algorithms such as coding. In that way, when we move from data space to model space, that is called inverse modeling, IM. That is called inverse modeling. So when we move from data space to model space, it is called inverse modeling. So under inverse modeling, we try to reconstruct the true model of the subsurface, or we recover the true model of the subsurface. That is what we do under inverse modeling. So what modeling helps us to do is to solve some issues that we may get when we go to the field. So before we go to the field, we use our laptop to do some simulation, to do some modeling, so that whatever we get in the lab, we can now go to the field to recover it or to demonstrate it. So that idea is modeling. Modeling helps us to save time, helps us to save cost. So before we just go to the field, we will have simulated what we are going to see on the field in the lab. So whatever results we get in the lab, we just go to the field to apply it. So that process is what is called modeling. And it can be forward modeling, where we assumed hypothetical model of the subsurface. Having assumed the hypothetical model of the subsurface, we now use that we measure some physical property of the subsurface. When we now get the physical property, if we now use that physical property to construct the true model or to recover the true model of the subsurface, that is what we call inverse modeling. Again, the idea here is to give you a broader view of what you are going to be seeing. So this course, Introduction to Geophysics, has touched everything you are going to learn up to your year 5. In detail now, you will now be learning them. So the essence of this course is to give you an insight into what you are going to be seeing from your year 2 to your final year. That is what this course entails. So by the time you finish this course, you are now having an insight into what you are going to be seeing. So like I said, this is also a course you are going to learn in detail before you leave or before you graduate from the department. So we also use modeling in order for us to save time, to predict what we are going to get on the field. Before we just go to the field, we will have done some simulation or modeling, we vary some parameter. Then by the time we reconstruct the true model, we see the true model we have constructed, we go to the field to now demonstrate it. So any issue that could arise, we could have needed that in the board with modeling. So that is what modeling entails. So on this note, we can bring the class to an end. So like I said here too, expect 20 questions from this aspect as well. So on that note, I think we can call it a day. If you have any questions, you can feel free to ask me.
In the modeling, is it like there's a, I don't know, there's like a software or app that you use and model everything?
You said?
I said when you are doing the modeling, you said you first simulate everything in your laptop. Is it like from your head that you are going to be thinking about the way it works, or is there like a software laptop app that
Yeah, it's a software. It's a software you must have in your laptop. It's a software that will enable you to do that.
Okay, sir.
It's a software that will enable you to do that. The software will allow you to vary some parameters, provided you have the license key to that software. So you will vary so many parameters, unlike the one they crack or the one they pirate. So with the licensed one, you have unlimited access to it. You can do so many things with it. You'll be seeing as you learn when you get to year 3.
Okay, sir.
Okay, any other question? Any question? Okay, if there are none, we can now, this is a fine point for us to end the class. Okay, thank you for your attention. So when the time for your test comes, I think it will be announced to you before your exam. Okay. Enjoy the rest of the day and of course the weekend ahead.